Hello everyone. There was a slight delay. I was not here, I was not in the studio, that's why it got delayed. Yeah, anyways, namaste Prince. Hello everybody. Next time I'll try to not to move out during these live session timings. Okay. Yeah. So today again we're back to our practice sessions. As per the schedule we're going, and it's today's turn is electrical machines, right? Electrical machines, PS Bhimbra. Can you all hear me? Just give me the confirmation whether you can hear me or not. Yes? Shall we go further? Shall we start the session? It's already got delayed, so let's begin. Yeah. So coming to the first question. Let's dive into the first question without any further discussion. Okay. Yeah. On screen now. Your first question is on screen. You can answer. Timer. I don't have the timer. Good, very good. Everybody have answered correctly. Good job. Smarter than what I expected. Quicker also. Good. That's simple rather, right? Question is very simple. That's why you answered very correctly. 1 and 2. Yeah. Nisha Kumar. Joshua. It's not 1 and 2, dear. Laminations are done. To reduce the eddy current losses. Only. Not only just 2, not 1. No 1. Okay? Okay. Good. Simple questions. This is from the book. It was question number 11. Okay? Because the questions what we're discussing is from PS Bhimbra. Okay? DC machines part. The question number was 11. You can just refer. Good questions are there. Yeah. Meanwhile, let's get to the next question. Timer has begun already. यार तुम लोग भी चेंज नहीं कर रहे हो, फिर भी यहाँ पे मंडे ही है. देखो फ्राइडे का शेड्यूल कल भी ऐसा था. Okay, good. Yeah, people are saying copper commutator segments are made up of. It's, see here, it's copper here also, it's copper here also. Which copper? Option 2. No, it's hard drawn copper. This is answer. 3 is answer. Okay? Yes, good. Most of you answered correctly. Next question. Yes. Maybe this time I'll give 60 seconds. Timer has begun. Read the question. It's easy, not tough one. It's easy one. All are basic fundamental questions. Fundamentally, you should be good. Basic fundamental aspects. Okay. Not any too much of analytical questions. Arjun, give it another try. Guys, hit the like, thumbs up. We're already late. I'm late from my end. Option 2. Okay. Option 2, option 3, option 2, option 3. People are getting confused between copper graphite and electrographite. Okay, I think you're getting confused between electrographite and copper graphite. So which one to choose? Which one to use? Which one to use? Electrographite or copper graphite? Or carbon? Yes, let me give the right answer. Right answer is this. Possible resistance of shunt field winding cannot be that less. If shunt field winding is this much less, then we have a shunt machine, okay, and let's take it as a motor or generator, anything consider. If here resistance is very small, then complete current will go here, okay, very less current will go here, very huge amount of current will drawn by the shunt field. So it cannot be this less, this less. Yes, series field winding will be less. Shunt field winding will be having more resistance. Okay. Now, as the time has come, so let's recall what is the cross-sectional area of shunt field and series field, conductor cross-sectional area. Conductor cross-sectional area, shunt field, series field, and armature winding. Tell me the sequence of this. Okay, tell me the sequence. Let me consider this one as X and Y and Z. Okay, which one is having, give it in an incremental order, ascending order. Ascending order. Tell me the ascending order of cross-sectional area. Those who are watching rebroadcast, give it in the comment. Okay, what is the ascending order of cross-sectional area of armature winding, series field winding, and shunt field winding? Which one will have less cross-sectional area? Which one will have more cross-sectional area? Ascending order. Less to more. X, Z, Y. Mansvi is saying. Anjanel is saying Z, Y, X. Dinesh is saying X, Z, Y. Okay. So here, answer is yes, you guys are right. X is having least cross-sectional area, X. Then cross-sectional area of X. Then next one is armature winding, Z. Then next one is Y. Okay. Because shunt field winding is carrying very less amount of current. Very less amount of current will be drawn by this. So we don't have to have a thicker cross-section area. We don't have to have a big cross-section area. Less is enough. Now, series field winding and armature winding both will carry the same current. Both will carry the same current. Armature and series both will carry the same current. Now tell me, how come you are saying this is less cross-section area compared to this? How come you are saying that? Tell me. Cross-section areas are, this is less, this is the sequence. How come you are saying Y is having highest cross-section area? On what basis? Yeah, give it a try, write in the comment. Yes. We can also give it in the comment box. Those who are watching not live, give it in the comment. You're lazy to write, lazy to type, you have to type some aspects. Okay, let me tell you. Field winding carries both currents. No, I mean to say field winding, and in this, see, let's take it as a long shunt, right? This is a long shunt. In the long shunt, armature and series winding both are in series. So whatever current flows here, IA is equal to ISC. IA is equal to ISC in this case, right? So current is same in both. So why you are saying this is having less cross-sectional area compared to this. Temperature of armature winding is less than series coil winding. No, that's wrong, Arjun. I mean armature current and field current. That's what. See, do you accept once with this condition? IA is equal to ISC. Yeah, current will be same. Yes, current is same. Cross-sectional area must be same, right? So on what basis you are saying ZY? Why can't it be XYZ? Obviously this is wrong. Turns are more, it's not about turns, we're talking about thickness of the wire, thickness of the wire. Which one is more thicker? Yeah, you have to think. You have to think like that. You have to think like that. Okay, let me take you to that answer. Let me take you to that answer. Careful, careful. See here, I'm drawing a series winding. I'm drawing a series machine. This is a series machine, right? So quite naturally, IA is equal to ISC. IA is equal to ISC. Current is same, but still cross-sectional area of series field winding is much greater than cross-sectional area of armature winding. The reason is, no, not armature hysteresis. Okay, careful here. The reason is, this armature, suppose let's take it as 10 amperes it is carrying. How much current? 10 ampere is a current. Okay. Let us take the parallel paths. Armature is having parallel path, right? Parallel paths are 2. Let us consider minimum parallel paths. 2 parallel paths it has. Wave winding, 2 parallel paths. Okay. A lap winding with 2 poles, 2 parallel paths. At least it will have minimum 2 parallel paths. Means what? Inside we have 2 parallel paths. Means each path is carrying 5 ampere and 5 ampere. This is 5 ampere, this is 5 ampere. So each conductor, each wire is carrying only 5 ampere. Combined it is giving 10 ampere, but each individual conductor is carrying only 5 ampere. So obviously the thickness which is required to carry that 5 ampere is much less than this thickness. Are you guys clear? Give it a thumbs up. Give it a thumbs up if you understood what I said. Give it a thumbs up. Quick. Have you got the point or not? Okay, good. So that's what. Whenever you get such questions, it's not just, you'll answer this question. You have to think a little bit. Okay, just this option is correct. Very less. Next one is electrographite brushes are used for 230 volt and 10 ampere machines. Okay, and copper graphite brushes are used for 230 volt and which one? Which one do we use? A copper graphite or electrographite? If we use that, why it is so? Why we use that? Why not the other thing? Yeah. You can say copper graphite is also as a metal graphite. Copper is a metal, right? Copper graphite, or you can say it as a metal graphite. Okay. Normally, these copper graphite brushes or metal graphite brushes, you can say, they are used for very less voltages. Very less voltages. Okay. Maybe 6 volts, small motors, DC motors you observe, right? 6 volts or 12 volts DC machines. Okay. For those machines, these copper graphite or electrographites are used. Okay, not for higher machines, because these offers very less drop, of course, copper, okay, less drops. So for 6 volts, the voltage itself is very less. If you use highest drop these brushes, then the output voltage will be very less. Poor regulation will be there. Okay, so we'll use this for only small machines. And electrographite, that will be having more friction, okay, and less sparking. We require less sparking there. Less sparking means it has to have little more resistance, because resistance commutation is a method. To get a better resistance commutation, we'll use this electrographite. Are you clear with this point or not? And obviously, yeah, this is right. Armature resistance also should be very less, not a high value of resistance. Very less resistance will be there, like a series field resistance. It's not necessarily exactly 1 ohm or something, maybe 0.1 ohm, it depends. Okay, are you guys clear? Shall I move to the next part? Next question. Yeah, somebody is saying something. Brush contact drop is less in graphite brush. No, no Shiva. Brush contact drop is more in electrographite. Okay, it's less in copper graphite. Okay, next question. Question number 14. This is a simple question. 20 seconds is enough. 20 seconds is enough. I have given a diamond rule regarding this in our machines course. In our machines course, I have given a diamond rule. You just go through the diamond rules. I have given 5 golden, perfect diamonds for machines, and 4 diamonds in case of networks. Yes, 50 hertz. Yes, 50 hertz. See, this thing always, as an electrical engineer, we should always remember 4-pole 1500 RPM means we should not waste our time even in calculating 120 F by P, or F is equal to P into N by 120. We should not waste even our time on doing this, because 50 hertz, this is a quite common thing. 4-pole and 1500 RPM is a quite common thing. Whenever you see that, you should mark this 50 hertz. Yeah, I'll tell you, those people who are answering 0 hertz, I'll tell you a point also. That's what a point to note here. The point is, though it is a DC generator, but inside the DC generator, the current flowing, that's what is inside the armature winding. In the armature winding, current flowing is actually AC. It's not DC. The commutator is there to convert AC to DC. Okay? In case of a generator, if it is a motor, DC to AC. So always in a DC machine, armature, current flowing is always AC. Okay? Yes. Okay. Clear? Not this, these answer. Shall we move to the next question? Question number 15. Yeah, again, I'm giving just 20 seconds. Yes, Ravi, I explained just now. Just to go back and check it. Ravi, I explained. Yeah, I can check it. Time's up for this. Yes, time's up. Normal DC machines operating at a full load conditions, the most powerful electromagnets. Yeah, only few correct answers. Good. I know most of you people, most of the students, when I ask this question, they would answer immediately interpoles, because the current carrying in the interpole is armature current, and also compensating winding armature current will flows. That gives a more flux. That's an apprehension what one would have. See, these interpoles are there to nullify a little amount of flux which is there in the M and A. Okay, though current carrying is more, but that does not give more flux. Okay, obviously field winding, we are keeping the field winding to create the flux. The best flux, the more the field winding flux we have, best is a method, best is a machine. Okay, stronger field is good. Okay, it's always this, not anyone. Okay, if armature winding flux is electromagnet is more powerful, then that's a disastrous. Armature reaction will be even more. Okay, always we should make sure that main field flux should be dominant of all. Okay, then if that is dominant, then nothing else can disturb DC machine. Okay, yeah, this is question number 15 from Bhimbra. Let's go to question number 16. Let me give, because you need to read, 40 seconds I am giving. Take 40 seconds time. Timer, you can see the timer here. Timer is running. Okay. Yeah, you can answer. Those who are watching rebroadcast, pause the video and answer it. You can, of course, you don't have to pause. Timer is running. Be quick in answering. This is a little basic analytical question, not a tougher one. Govind is saying 2, Anusha is saying 1, Manasvi 4, Shiva 1, Dinesh 3, Ramesh 1, Ashish 3. Okay. Let's see. A self-accelerated shunt generator fails to build up because why? The self-accelerated shunt generator, why it is failed to build up the voltage? Okay, I think you must recall now, whenever you get this question during a practice session, you have to recall, okay, what is a voltage build up process, how voltage will build up, you have to recall, okay, not when you are giving answers, but yeah, when you are practicing, okay, when you are practicing, you have to think the surrounding aspects, in and around there will be some aspects, you need to recall all those aspects. That's how your brain will be trained enough, whenever you get that question, your brain will be trained enough to recall quickly those aspects, okay, yeah. It fails to build up, field circuit is open, obviously field circuit is open, field current will not flow, so there won't be any further build up of voltage. Yes, this is right. Armature circuit is open, if armature circuit is open, that's also true, yeah, right. Residual magnetism is absent, yes, this is also right. We need to have residual magnetism, and direction of rotation is also wrong. You have to have the new EMF. We have a residual magnetism, but the new current, whatever is flowing, new flux will create, and both must be in the same direction. If both are in opposite direction, then there won't be any, resultant flux will be 0. So if the direction of rotation is reverse, then the new flux will be opposite. So you will get resultant flux 0. Okay, yes, most of you answered correctly. 1, 2, 3, 4. Yes, direction of rotation also matters because that changes the current direction, right? Clear? Yeah. Next question, question number 17. This is a tricky one. Okay, I'm giving 60 seconds to this. This is a tricky one. Don't be in a rush to answer this question. Those who are watching rebroadcast, type your answer, question number 17. Underscore what is your answer, give that answer, okay, give it in the comment. Yeah, I said right, don't be in a hurry, don't be in a hurry. Few people have answered correctly. The first one to answer is Manish. Manish has answered correctly. First one. And yeah. Yes, absolutely right. Time's up anyways. No voltage will build up, 0 volts. Just now I said in the previous question, I said I linked that here. A DC shunt generator build up to 230 volts is generating. Okay, 230 volts it is generating, DC shunt generator is generating 230 volt. Careful here. Okay, I have a field winding like this and the connections are like this. Okay, it is giving 230 volts and it's running in one direction, okay, clockwise direction. So current flowing in the IA current is like this, because one direction EMF will be, maybe let's take it EMF is upward, I mean positive plate upward and negative plate downwards, then current will be like this. Okay, the moment I change this direction, we change the direction, everything is done, so we stop the machine and we change the direction here. So when we change the direction of rotation, so EMF direction will change. EMF is downwards, so current direction, new current direction is downwards, so shunt field current is now in this direction. So previously current was flowing in the shunt field in one direction, that has created a residual flux, that has left some residual flux in one direction, maybe upward or downwards, okay, in one direction. Let me take it as upward. Now because of this new current, the new flux whatever is generated, that is opposite to this, because current direction has changed, the flux direction also changed. So both will be subtractive in nature, nullified, net flux has become 0, so it won't build up any voltage. Okay? Yes, most of you answered, but yeah, 50-50, some people have answered 230 also. Try to be careful, try to be careful. Yeah, let's move to the next question. Question number 18. This is also a tricky question. Take 60 seconds, read properly and answer it. Those who are watching rebroadcast, give Q18 underscore your answer. Okay. Thumbs up, give it a thumbs up. We're having sessions, but you're enjoying, you're learning things up, but you're not hitting a like. Give it a thumbs up in chat box. Okay. Those who have liked the video, when I ask you to give a thumbs up, at least give it a thumbs up in the chat box. Just click right, MOC. So then we'll get some energy. Okay, energy. I need some energy. Answers, yeah, that's good, but energy also. No energy you want to give? Okay. I lost my energy. Yeah, I got one energy. Okay. तुम्हारा energy नहीं मिलेगा. Yeah, मिल रहा है. People are giving. Yes. Answer is 3. See, careful here. Interesting aspect. Analytical question. You need to analyze a bit. A separately excited DC generator running at a rated speed has 6 volt across its armature terminals. A separately excited generator. This is the best generator ever in the world. Really. Yes, it is true. If it doesn't have a commutation problem, then I don't think further development would be required on any generators or motors. Wow, Nagarjun Reddy has given so many thumbs up for you. Okay, so now it's running at rated speed. It's running at rated speed across its armature terminals, and 6 volt is developed. 6 volts. When there is no current here, when field current is 0, it is 6 volts. Okay. It is just because of a residual flux. It is just because of residual flux. Okay. Those who have said answer 3, more than 6 volts, tell me why it is more than 6 volts. Meanwhile, you write. Okay. Yes, this is right answer. But why it is more than 6 volts? You type. I'll see. I would like to see that. Okay. Yeah. So when field winding is excited with 1 ampere, so this is done. This is the first case. In the second case, what is done? In the second case, field winding is excited to 1 ampere. Okay, field winding is excited to 1 ampere. Then voltage has built up to 250 volt. Then voltage has built up to 250 volts. Okay, at no load again, no load connected. It's done. Case 2 also done. Next again, case 3, again field current has reduced to 0. Again field current has reduced to 0. Now what will happen to this 250 volt? Will it stay at 250 volt or will it come down to 6 volts? Or will it be less than 6 volts, or will it be 6 volts, or will it be more than 6 volts? That's the question. So answer is definitely more than 6 volts. It's because, tell me, not residual flux. Residual flux is already there. Residual flux is already there. Tell me why it is. Because of the residual flux you have 6 volts. Now, why in the third case, why at case 3, why you are having more than 6 volts? That is a question. Okay, that's how you need to think. Those who are watching rebroadcast, type in the comment why it is reason. No, any guess? Not a guess. Yeah, okay, give it a guess at least. What could be the possible reason? One guess we got residual magnetism. N is equal to E by pi. N is equal to E by pi. I didn't get it here. Yes, it is due to pole shoes, no load. Yeah, partly Gautam was correct. It's due to the hysteresis effect. It is due to the hysteresis effect. If you see, at the beginning we have some residual flux is there, okay. So let's see, residual flux is here, the residual flux is here. Now after some time, maybe after 10 days, after maybe 20 days, what will happen to the residual flux? Residual flux is slowly coming down, because residual flux will not be there for lifelong, right? Residual flux will come down, okay. Now the moment it is again charged with some voltage, due to the hysteresis effect, due to the hysteresis lag, yes, it stops here. It will not follow the same path. It will not follow the beginning. At the beginning, it is starting from this path. Due to hysteresis lag, it won't follow the same path. It will follow this path. It will follow a little higher path. Okay, that's what hysteresis lag. Okay. So answer is, so as residual flux is a little more, or you can say due to the hysteresis lag, that flux has added up, so you'll get more EMF, little more than 6 volt. Okay. Good participation. Good tries. Question number 19. You take here 40 seconds is enough for this. Yes, good. Timer is running. It's inertia node here. We're talking about a generator, right? If it is a motor, then you can even think of it. Three. Shubham, good. Share it with your friends also. Give it a thumbs up, like, share, love and comment. Time's up. Like, share is okay. Love and comment, okay. Yeah, it has come out of my mind. I said it. A DC shunt generator, when driven without any excitation, okay, showed an open circuit voltage of 12 volts. Okay, 12 volt has come because of the residual flux. So it is clear, till this it is clear. See, this is how you need to understand, you need to answer the question. First you will read this line. Without any excitation, it has shown open circuit voltage 12 volts. Means what? Residual EMF is 12 volts. So I don't have to read this line once again, because I kept this entire information in this. When the field winding is excited, the voltage drops to 0. Why? That's a question. Field resistance was higher than the critical field resistance. What is a critical field resistance? This is a field resistance, and critical field resistance is tangent. This is a critical field resistance line, and this is OCC. Okay, this is a voltage and this is a flux, field current IF. Okay, so here this is having more slope, this is having RC is more slope, so this is more. Okay, this is the operating voltage. So RC field resistance was higher than the critical resistance, and there was no residual flux is there. Residual flux is there already. That's where 12 volts has come. So this is not answer. Field winding was wrongly connected. This could be possible answer. There was a break in the armature circuit. If there is in the armature circuit break, you will not get 12 volts, right? So this cannot be the answer. Now field resistance is higher than the critical resistance. If suppose field resistance is higher than the critical field resistance, then it will stay, the output voltage will stay at 12 volts. It will not come down to 0. Of course, it fails to build up. Under this condition, the voltage build up will not happen. That is for sure, because always for the voltage build up to happen, this should be the case. Means RF should be less than critical field resistance. Okay. But it is said it is not failed to build up. In this case, if this would have happened, again I am repeating, the output voltage would have maintained same 12 volts. But it is said voltage is dropped to 0. Voltage is dropped to 0 because field winding is connected reverse. So current flowing in the field winding is flowing reverse. So the new flux and the old flux are opposite. So it has dropped to 0. Yes, this is the answer. Clear or not? Careful. Don't get confused with this. Some people are answering this also. Yes, that could be a good confusion. But yeah, you should be now able to understand why it's not the case. Guys, clear? GE1, Sharada, Manikanta, are you clear with this? Okay. Last question of the day. Question number 20. You take 60 seconds. 60 seconds and answer this. Maybe I'll have to give more time, I think. I'll reset again at 40 seconds. Yeah, I'm resetting it because it might require a little more time. Yeah, good. Share it. If you like, immediately you got the good explanation. Thumbs up. Taste the thunder. That gives good energy, right? You're watching, you're getting something. I should also get something in return. At least your thumbs up will give something return to me. Yeah, it is. Thumbs up. Don't say I already hit the like button, sir. Okay, that's okay. But here in the live chat, if you give that thumbs up, that's also a good thing. That also gives good energy to me. Your one thumb is energy. Yeah. Boom. Time's up. No answer we got. In previous question, why not A? What the bloody hell? I explained such a long story just because of that. Yeah, dear Rajia, dear Shubham. I explained that. Just in the rebroadcast, you watch it again, you will understand it. Yeah, finally we got answer. Dinesh has answered. Good. Yes. You're right, Dinesh. So, you're the only one who has answered these questions. So, today's winner, you're the today's winner because you answered correctly for this question. You are the only guy. And I saw you following regularly, right from the beginning of following the sessions. So, you give your email ID now, okay, and we'll give one test series, select any one test series from exam.pit.in. We have some test series in this exam.pit.in. Others also you can purchase, they're just at very less price, okay. Dinesh will assign this one test series for you free. Give your email ID in the comment right now in the chat box. Give your email ID so that we will email you an exclusive coupon to get the course, to get the test series for free. Okay. Others you can visit exam.pi2.in. Okay, Dinesh, we got your email ID. Yeah. We got your email ID. Likh lena. Yeah. Yes. Now, coming to the answer. The DC shunt generator is having, yeah, good. Perfect. In one shot, Anusha has said, critical field resistance. Is it inversely proportional to the speed? No. 80 ohms, see here, it's not inversely proportional, it's proportional to the speed. Careful, it's proportional to the speed. This is the OCC. First case, 1000 RPM, 1000 RPM, this is the OCC. Okay, OCC at, careful here, OCC at 1000 RPM. The corresponding critical field resistance is tangent to this, somewhere over here. This is RC1. Now, critical field resistance, this is how much? 80 ohms. Due to, sorry, here it was given that DC shunt motor is having shunt field resistance of 50 ohm was generating normally. Yeah, fine, fine. So, when it is when field winding resistance is, this is RF, which is equal to 50 ohms. So, RF is 50 ohms. This is the first case. Till here, this is a diagram. Till here, this is a diagram what I had drawn here. Okay, 1000 RPM and RF is equal to 50 ohm and corresponding critical field resistance is 80 ohms. Now, let us understand further. Due to some reason, the speed of the prime mover has become such that generator just failed to generate. Generator just failed to bloody generate. Means the new speed has become like this. Speed has come down so that it has just, now this RF line has become tangent to this. Okay, this is the new speed. Now what is that speed? What is that speed? Okay, so we can consider now for this corresponding speed, this is a critical field resistance. For this corresponding speed, this is a critical field resistance. This line, we can consider like that, that 50 ohm is a critical field resistance. That's why it has just failed, that field resistance has become critical field resistance now for this speed. So it has just failed. So for 1000 RPM, 80 ohms, for 50 ohms, how much RPM? That's it. Simple bachpan ka question, childhood days question. Definitely this is not the answer. 1000 volts speed is less. 80 ohms is 1000 RPM. 50 ohm is how much RPM? Okay? 50 ohm is how much RPM? Proportional. So you'll get it, how much? 1000 into 50 by 80, you're going to get this. Yes, lot of exciting explanations, lot of exciting animations you will get from machines, lot of exciting experimental analysis we developed in our machines course. Okay, and even power electronics course, in the networks course, lot of good analogies you're going to get. It's not just bloody understanding and answering a question. Of course that is important, but along with that you have to have that confidence, right? So you will definitely going to get that confidence once you see, once you take the course. Okay, enjoy the course. People are enjoying, join that enjoy committee. Okay, enjoying community of the courses. That's it for this session. Thank you all, love you all, see you all in the next session. Okay, have a great day.